invitation. That's a great pleasure to be at this conference. So I don't have my title page right now here, but what I want to talk about is the variance of the Erdős discrepancy problems in over the function field. And what I want to begin with is to tell you a couple of words about the classical problem. So the problem that actually motivates this talk is the well-known conjecture of Erdős that if you take any sequence of plus minus ones and you look at the discrepancy along the homogeneous arithmetic progressions, that is, you take your favorite d, you take your favorite length, and you measure the sum over these progressions, then the conjecture says that this discrepancy should be actually unbound. And so that's been a subject of the Polymath project in 2010, and before 5 years ago, the state of the art was that instead of infinity, we had a bound 2, which has been done by a massive computation, really. Okay, so the situation changed in 2015, and in 2015, Terry Tao, he actually proved the Erdős discrepancy problem, proving that the discrepancy is actually unbounded. But the main important thing, I will not talk about the proof here, but what I want to focus on is the two main ingredients here. And the two main ingredients, one of them was that the Fourier analytic reduction of this problem to the very special class of the functions, and those functions are completely multiplicative functions. So in particular, I'm just going to remind people that the completely multiplicative functions, those are functions that preserve the multiplication. So instead of proving this conjecture for all functions, it's enough to just consider this class of functions. And for these class of functions, you can see that the partial sums, you can always factor out f of d, and the partial sum simply becomes, the question of the discrepancy becomes the questions of the unboundedness of the partial sums. And well, there has been, right before that, there was a spectacular breakthrough by Matamaki and Radziwiłł that Tao used with extra ingredients to actually resolve to treat this case of completely multiplicative functions. Okay, so what I want to do is I want to discuss the analog of this and over the polynomial rings and actually show some features, interesting features that are present there. So perhaps I should remove this. So, but before that, the motivating question for me would be, okay, so we know the discrepancy is unbounded, but how small can it be, really? So for the multiplicative function, how small can the partial sums be? And here the instructive example to keep in mind, of course, we would like to take it to be a character, but character is not allowed because there is a 0 there. So what we're going to do is we're going to take something which looks like a character. Namely, we will take a, say, character, modified character of modulo 3, where there is 1, where p is 1 mod 3, and 2 minus 1 with 2 mod 3. But at minus 1, we're going to, instead of 0, take it minus 1. And what one can see here is that if one computes this, and I will do it a bit later, then such partial sums can get as large as log occasionally. So the guiding conjecture in this field is that this actually should be in extremal examples. So namely, the smallest discrepancy should be log x, and it should attain on the modified characters of prime power conductors. So let me just write it down a bit more precisely. So what I mean is that if I happen to find a completely multiplicative function with the partial sums which grow not faster than log x, then this happens if and only if f is a modified character of the prime power conductor. Namely, you just change at one prime value at plus or minus 1. So this is completely open, and I would like to look at this over the function field and see whether we can do something there. Okay, I hope that's okay. Okay, so what is the setup there? So we start with the polynomial ring. So you fix your favorite of Q, and you look at the set of monic polynomials of degree n, and and Pn. This is the set of polynomials of degree n. So M is the set of polynomials of all degree, actually, not Mn. And the question here is that, okay, so what is the multiplicative functions over the function field, or what are the functions in general? Well, this is just a function that preserves the product of polynomials, so there is nothing special about it. And so what is the question then? Well, the question is that how do we define the partial sums? Well, the partial sums you can define in many ways, but one of them is to take polynomials of degree up to n, or degree n, and look at the corresponding sigma of f, which is the partial sums. So notice here that I took it to be equal to n, but really the number of polynomials of degree n is so much bigger than the previous one that those questions are completely equivalent. And what is interesting here is that already in Polymath 5 project, the people that were there, they actually noticed that there exist completely multiplicative functions for which these partial sums defined in this way are actually bound. So they said that the question there, the discrepancy problem over a function field, is not really true, and maybe it doesn't worth studying it, or actually it does worth studying it, but not clear what is the formulation. And if you think about that, so what would be the immediate fix to this question? Well, the problem is that when we look at polynomials of degree n and polynomials of degree n plus 1, the step from n to n plus 1 polynomials, at one time we add enormous amount of new polynomials of degree n plus 1, which we have full control over, at least prime polynomials of degree n plus 1. So the fact that we can cook up a lot of bounded sums, it's not really a surprise. So it's simply because these sigma f's do not measure it very well. So the immediate fix to that would be to look instead at the short sum discrepancy. So over the number field, over the integers, if you have that the partial sums are unbounded, then clearly the short sums are unbounded as well. And this measure of short sum discrepancy is much better because there is more short intervals than long. So, but what is the short interval over the function field? Well, the short interval over the function field is a very simple notion, is that we just look at, for each polynomial f naught, we look at all polynomials that differ from this polynomial by at most h coordinates. And that's going to be an interval of length h. And then the immediate question is, right now we have many, many more short intervals, and we can hope to get better understanding of the discrepancy. So then the immediate question is, what about the short sum discrepancy of f? And unfortunately, one can look at the same example as we just had in number field. We could have taken the characters everywhere except one prime. And for this function, what will happen is that the discrepancy, if we look at this supremum, it will still be big O of 1. Okay, so let me look at the time. I'm doing okay. So the first theorem that I would like to tell you about today, and what I'm going to do, I'm going to stop sharing this and perhaps write from now on. So the first theorem that I would like to tell you about today, this is the joint work with Sasha Mangerel. And Jouni Teravainen. I keep putting pluses there. So the idea is that the main result is that these modified characters are the only counterexamples over the function field. And so let me just state it properly, that if I give you a completely multiplicative function, which takes value plus minus 1, and I look at the discrepancy, so I pick my favorite center, I pick my favorite length, and I look at the sum of my function around this point, and that happened to be bounded, then what is true is that it happens if and only if f is a modified character of the prime power conductor. So where it is defined in exactly the same way as before, this is mimics the character on all primes except prime p, where you can have plus minus 1. So this is the function field version of the conjecture. However, if you remember the conjecture that I started with, the special case here over the number field, I had here the log x. And here I have a bounded discrepancy. So what is the difference? I want to, in a couple of words, to explain what is actually causing this difference in terms of the quantitative bounds. Because you can see that the formulations are the same. The extremal examples are the same. So here is what is happening and what is really causing the difference. So I'll put the remark here. And before I explain this, I just want to go back to the example of this chi3, which was a character which was 1 when p was 1 mod 3, and minus 1 when p is 2 mod 3, and again 1, say, or plus minus 1, doesn't matter, when p was 3. So the reason, if we try to compute discrepancy for this character, so let me just try to compute the partial sums of this guy. So if I were trying to compute this, clearly what I would do first is I would factor the highest power of 3, because this is the problematic power. So there is at most log x over log 3 of such powers. But the sum inside, this is nothing else but the sum up to x to the 3 to the k. And since I factor out the power of 3, the rest looks like exactly like a character. So this is just a character mod 3. And so what we can see immediately here, that this sum is just the sum of the character, which is big O of 1. There is at most log x of these terms. So the discrepancy is as big, it can be as big as log x. But occasionally it can get as big as log x, because what we can do, we can match these power and the character sum by picking up the right digits in ternary expansion of n. So the important thing is that it can occasionally get as big as log x, simply because the intervals of this form contain different number of remainders modulo 3. So this feature is not present in the function field in this type of formulation. So key difference in the function field is that all short intervals contain the same number of remainders modulo some prime power, modulo some prime when your degree is big. It just doesn't see the difference in the modulus. And therefore discrepancy drops exactly one level down. There is not this log x and it becomes bounded instead. But all of the rest of the phenomena do happen. So the key difference between function field and number field in this formulation, the short intervals contain different number of residues, mod, say, some prime. But in general, these are exactly the same statements, morally speaking. This is exactly the same extremizers. Okay, and now that could have been the end of the story, but I still have like 10 minutes to talk about. And I would like to talk about, that could have been the end of the story, if not the question of Yuru Lu and the next speaker after me in this section. So the story turns here, and there is a beautiful question that actually motivated a lot of work after that. The question of Lu and, well, I guess independently, Trevor Woolley. So the question is the following. Okay, well, but maybe we proved some result, but there is a difference between function field and number fields. So perhaps we are asking the wrong question. Perhaps we are measuring the norms in the function field in the wrong way, or not the appropriate way for this problem. And what they ask is that what is the right formulation of EDP if we change the norm over the function field? So, and more precisely, what is the discrepancy of the sequences in what is called lexicographic ordering? So they use this ordering. So they use this ordering to study worrying problem over function field. To study worrying. So let me explain what is that order I'm talking about here. So the order comes from the following. So we want to rectify this problem that the short intervals do not have different remainders. So to order, how can we order polynomials? So one way, the first thing what I want to do is I want to take my favorite FQ and order my FQ. So ordering FQ is very simple. One can take any map between the elements of FQ, say bijection, to 1 to Q minus 1. So they took a very, for their study, they took a very particular one. They took a generator and of FQ and just order it according to the power of generator. But now, how can you measure the norm of the polynomial? So if I give you the polynomial, monic polynomial x to the n, a1 x to the n minus 1, plus a2 xn minus 2, blah, 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 am. Then, and I have this order phi, then the way I can compute the norm is that I can just evaluate this polynomial at the point q. But instead of a1, I'll put just the order of a1, and I'll put just the order of a2, and I'll put just the order of am. So that will be the ordering of the polynomial. And this is the lexicographic ordering, which is the natural ordering of the polynomial as the ordered set. So let me put the remark here. What is the benefit it is to us? Well, the first benefit is a strict order. Before, all polynomials of degree n had absolutely the same norm, which is not good. So this is a strict order. And what they did before, Lu and Trevor, is that they actually studied the properties of this norm up to some point that they needed. And it contains the prime number theorem inside. It contains the expected number of primes in the intervals and so on and so forth. So it does satisfy the natural arithmetic. But one thing which makes this much harder to work with and than the original problem, even the problem over number fields, is because this norm is not multiplicative. And this, which makes it so the life much, much more difficult, at least for the problems that I'm talking about. So the fact that this roughly quantitatively behaves as well as we need, the short intervals here, because of this extra randomness, will have different number of remainders, but there is a problem of non-multiplicativity. But the next theorem that I want to tell you about is that, so what is the answer? What is the EDP version if we order polynomial in this way? So here is the theorem. So this is the same set of us. I don't even know what to put it here. Maybe I should put like 225 or something like that. But okay, we are trying to finish it up, but I hope it's going to be out very soon. So the statement is very simple. So I take any sequence in FQ of x, and I look at the original EDP formulation. So I take my favorite arithmetic progression, take my favorite difference, take my favorite length, and I look at this supremum over all polynomials, and now the length is given by how much I multiply it. So f, the norm of f in the order phi less than n. So this discrepancy is going to be infinite. So in this norm, the EDP is right, is true, and that is actually the upshot here. Okay, so this norm turns out it's much more suitable actually for problems where if you want to compare the situation in number fields and function fields, where you actually care about this arithmetic of the short intervals, modulo numbers. Okay, I won't talk much more about that, except that I want to, maybe in the last three, 4 minutes I have. So I want to go back to the original actually question. And the original question which we started with was the polymath project question, an observation that actually sigma f, the partial sums up to degree n, they can be bounded for some functions. And in that polymath project, so there is a question of Gil-Kallai in this polymath. So he asked whether, okay, well, we can have that these discrepancies are bounded, but can we classify such f? And I want to tell you one theorem in this direction. So as stated, this is absolutely hopeless because one can produce, as I already said, that there is this gap between level n and level n plus 1. So you can produce uncountably many counterexamples to that. So the question of classification would be more meaningful if you were restricting yourself for some class of functions of f, where you can actually say something. And I want to restrict to a very simple class where we can do something in function fields, but we cannot do over number fields. So it's an open question in the case of integers in particular. So here is one theorem, which I have, again, surprisingly the same. Will not put the date. So let's look at functions which are modified characters, and now not prime power conductor, but any conductor Q. So now I have IQ might have a couple of divisors, and on each of them I can put plus minus 1 as I wish. And the question becomes, well, can we at least say what is the discrepancy of these simple functions? So in number field, this is an open question, the exact discrepancy, and I want to tell you what one can say in function. So, and the guy who is going to be responsible for this discrepancy, and this is the feature which is not present in number field, is this interesting polynomial. So everything will depend on the polynomials. So I take prime divisors of my modulus Q, and I subtract f of p conjugate. So it's valid for complex valued functions. So then what I can say is that I look at the highest multiplicity of the root of this polynomial p of z as a complex polynomial. If all roots are simple, and we can understand when it holds, if all roots are simple of p of z, then the discrepancy is bounded. But if B is the maximum multiplicity, then it happened to be that the discrepancy is omega n to the b minus 1. I'll stop here. This is exactly 25. And this is open. We can't do that in number field. We don't know part 2. and there is no such polynomial, but we can do something here. Thank you very much for your attention. Oh, I can't hear anything. Is it my problem?
Oh, no. So thank you very much. We have a minute or two if there are any questions for the speaker.
Perhaps I can say that there will be another, since there are no questions, there is another talk on Thursday, and there is a related work, there is a work, another feature of discrepancy problem. So we have function field right now, number field, and there is also diversion in FP. And there is a recent work by Jacob Fox, Shu, and Zhou, and I think there will be talk on Thursday about that. So I recommend, this is about FP version, FQ version of that, and there are surprises there as well.
Okay.